This is tutorial 3, and we will cover chapter 4 from the textbook, Number Theory and Cryptography. We will be working with the integers and cover topics from number theory, and one of the applications we'll be looking at is cryptography, which is and the application here involves coding messages. Starting with the integers and division, we have some definitions. Division, we start with A and B are Z. Z, of course, is a set of integers with A doesn't equal 0. So we say that A divides B. طبعا this symbol here is not normal, it's not division. We're not dividing A by B. This just says that E divides B. معناتها A is a factor of B, or that B divided by A is a whole number. But again, this is A divides B, or A is a factor of B. A is a divisor of B. All that means the same thing. طبعا that means that B is a multiple of A. To say A does not divide B, we use the same technique, is that we use the same symbol but we cross it. So this should be read as A does not divide B. If A divides B, we can use a quantifier by saying there exists a C such that B equals A times C. But here again, that also says the same thing, and that A is a factor of B, or that B is divisible by A. And the domain here for this quantifier is the set of integers. Here are examples. 3 divides minus 12, because minus 12 divided by 3 gives us minus 4, a whole integer. Or you can write minus 12 as minus 4 times 3. Okay, then 3 divides minus 12. This is a true statement. If you write 3 divides 7, this is a false statement. You can also write it as 3 does not divide 7. Here we have 3 formulas that are true about division, and these formulas will be used later when we look at division as a relation. So here A, B, and C are all integers. The first rule, if A divides B and A also divides C, then A divides the sum, B plus C. And here is an example. We know that 3 divides 12, and also 3 divides 9, so it must divide their sum. 3 divides 12 plus 9, or 3 divides 21, and طبعا this is true because 21 divided by 3 is a whole number, it's equal to 7. The second rule, if A divides B, then A divides any multiple of B. But A divides B times C for any C. But if A divides B, then A divides B multiplied by any other number. And that makes sense because if A is a factor of B, then it will be a factor of B multiplied by another number. And here is an example. 2 divides 6. That means 2 will divide 6 multiplied by any other number. For example, 2 will divide 6 times 3. 2 divides 18. Of course, this is true because 18 divided by 2 is equal to 9. The third formula, if A divides B and B divides C, then A divides C. These are 3 numbers. The first divide the second divide the third, then we conclude in the first one divides the third number. If A divides B and B divides C, then A divides C. Here is an example. 4 divides 8 and 8 divides 64. Therefore 4 must divide 64. And is this true? It is, because 64 divided by 4 is equal to 16. Next, we would like to look at the division algorithm. If a is an integer and d is a positive integer, then there exists a unique integers q and r such that a is equal to d times q plus r, and r is greater than or equal to 0 and less than d. What the division algorithm tells us is you can take any integer and divide it by a positive integer. The result will be a quotient, a whole number, plus a remainder. And the remainder will be non-negative, to be greater than or equal to 0, and less than d, less than the number that you are dividing by. فهير طبعا يعني q here we call it the quotient, and r is the remainder. D is called the divisor, يعني because you are dividing by d. A is called the dividend. And again, q is the quotient and r is the remainder. So to restate the division algorithm, you can divide any integer by a positive integer. The result will be a quotient and a remainder. And of course, you can always write a as equal to d times the quotient plus the remainder, and you can divide in a way that the remainder is always non-negative, it's greater than or equal to 0, and less than d. We use short statements to describe the quotient and the remainder because these will be used later in the application. For the quotient q, we refer to it as E div d. So A div d. What that means, q is the quotient that you get when a is divided by d. The remainder r is referred to as a mod d. So then r is the remainder you get when you divide a by d. A div d refers to the quotient, a mod d refers to the remainder. Here are examples. What are the quotient and the remainder when 101 is divided by 11? Probably the easiest way to do this is use long division. When 101 is divided by 11, you get 9, and the remainder is 2. Once you determine the quotient, which is 9, then multiply the quotient by 11, which is 99, subtract it from 101, the remainder will be 2. Here we are dividing 101 by 11, the quotient is 9, the remainder is 2. And you can write 101 as 11 times the quotient, which is 9, plus the remainder, which is 2. With the new terminology, q is just 101 div 11. It is the quotient you get when you divide 101 by 11, and that of course equals to 9. R is the remainder, so it is 101 mod 11. It is the remainder when you divide 101 by 11, and it is equal to 2. Another way to look at this division is that the quotient is equal to 101 div 11. Using the floor function, this is the floor of 101 divided by 11. Yani, when you divide, you will get a number with a decimal. If I take the integer part of the decimal, that will give you, the division will give you 9.18, which is not a whole number, but take the floor of that, which is equal to 9. Take the whole number that you get from the division, this would be the floor of 9.18. Again, the quotient can be obtained by evaluating the floor of 101 divided by 11. This is the floor of 9.18. The largest integer less than or equal to 9.18 is equal to 9. That gives you the quotient. How do you find the remainder? Multiply 9 by 11 and subtract it from 101. You get the remainder, which is equal to 2. Here are more examples. Now you have to be careful. Now we can divide any number by a positive number. If both numbers are positive, normally there's no problem. But if you take a negative number and divide it by a positive number, you have to be careful that you must divide in a way that the remainder is positive. So here is another example. What are the quotient and the remainder when minus 11 is divided by 3? The correct way to do this, when you divide minus 11 by 3, the quotient should be minus 4. Minus 4 times 3 is minus 12. If you subtract minus 11, if you subtract minus 12 from minus 11, it becomes minus 11 plus 12, which is 1. The remainder is 1. This is now dividing in a way that the remainder is 1. This is the correct way. Now your quotient is minus 4. Your remainder is equal to 1. It's not, here is, you might do this, but this will not give you the correct remainder. Minus 11 can be written as 3 times minus 3 minus 2. The equation actually is correct, but it does not give you a positive remainder. If you do this and conclude in a minus 3 is the quotient, this is wrong. Then you did not get a positive remainder. This is the correct way to do it. Minus 11, when you divide it by 3, you should get a quotient equal to minus 4, and the remainder is minus 11 minus 12, which will give you 1. Quotient is equal to minus 4, remainder is equal to 1. Here is the quotient and remainder using the floor function. Q, which is the quotient, is minus 11 div 3. This is the floor of minus 11 divided by 3. This is the floor of minus 3.6. The floor of minus 3.6 is the largest integer to the left of minus 3.6, and that will be minus 4. But this is your quotient. The remainder, take minus 11, subtract minus 4 times 3. This is minus 11 plus 12, which is equal to 1. This is minus 11 mod 3. And again, be careful if you are dividing a negative number by a positive number, that you should do it in a way that the remainder has to be positive. Here is using the mod and div terminology to solve equations. Find a and b if the first equation 2a plus b equal 46 mod 7. The second equation a plus 2b equal 47 div 9. For the first step is to replace the right hand side of each equation by its value. What is 46 mod 7? Here we are looking for the remainder. If 46 is divided by 7, we will get 6, and the remainder is 4. So you can replace the right hand side in the first equation by 4. The first equation becomes 2a plus b equals 4. This is just replacing 46 mod 7 by 4. The second equation, the right hand side is equal to 47 div 9. Here we're looking for the quotient when we divide 47 by 9. 47 divided by 9 equals 5, and the remainder will be 2. So you can then replace 47 div 9 by the quotient, which is equal to 5. Then in the second equation, the right hand side becomes 5. Now this is two equations that you can easily solve using algebra. For example, if you take the first equation, subtract 2 times the second equation, you will get minus 3b. If you subtract this by 2 and subtract it from the first equation, the a will cancel, minus 2a will cancel. You're left with minus 3b equal minus 6. Divide by minus 3, b is equal to 2, and then use either equation. You can substitute b equal 2 in the second equation, and you will have a is equal to 1. فthis is a solution of those two equations, a system of two equations. طبعا this is the main thing was to يعني evaluate 46 mod 7, which turned out to be 4, and 47 div 9, which turns out to be 5. طبعا the mod, as we said, is the remainder, and the div here is the quotient. The remaining thing is just solving linear equations, which is a subject of algebra. Next, we would like to use a division defining a relation. This relation will be studied more in the chapter 8, I think, when we study relations. But for now, we would like to define the modular congruence, and using the modular congruence, we will look at an application. For here, a and b are integers. M is the positive integer that will define the congruence. For a and b can be any integers. M is fixed for one relation. M is a positive integer that will define the congruence relation. We say A is congruent to B modulo M, and we write it like this. A is congruent, here, this is the notation. We say A is congruent to B mod M if and only if one of the conditions is satisfied. Either A mod M is equal to B mod M, or M divides the difference, A minus B. طبعا M divides A minus B means A minus B mod M is equal to 0. The first condition, A mod M equal B mod M, that means the remainder I get when I divide A by M is the same remainder when I divide B by M. You get the same remainder. The second condition is easy, that M must divide A minus B. فإذا the congruence, A is congruent to B mod M if one of these conditions is satisfied. And normally the second condition, one of them is sufficient, one of the conditions sufficient. Whenever either of the condition is satisfied, the second one will also be satisfied. And normally it's easier just to apply the second condition, that A is congruent to B mod M if A minus B is divisible by M, or M divides A minus B. Let's look at examples. Is 17 congruent to 5 modulo 6? To apply the first condition, 17 mod 6 is equal to 5. Then if you divide 17 by 6, the quotient will be 2, the remainder is 5. Mod is the remainder. If you divide 17 by 6, the remainder is 5. What about if you divide 5 by 6? Anytime you divide a number by a larger number, the quotient is always 0, and the remainder is the number you started with. For 5 mod 6, the quotient is 0, the remainder is 5. For 5 mod 6 is equal to 5. Then the first condition is satisfied. 17 mod 6 is the same as 5 mod 6. Then the two integers are congruent. 17 is congruent to 5 mod 6. You will see in the second condition is also satisfied, that 6 is the positive number that determines the congruence. 6 must divide the difference. 6 divides 17 minus 5. That means 6 must divide 12, and 6 does divide 12, because 12 divided by 6 is equal to 2, a whole number. Then either condition is satisfied, and only one of them is needed. Then the conclusion is that 17 is congruent to 5 mod 6. Here is the second question. Is 24 congruent to 14 mod 6? Here 24 mod 6 is equal to 0. In fact, because 24 is divisible by 6, If you divide 24 by 6, the quotient will be 4 and the remainder is 0. 24 mod 6 is just equal to 0. What about 14 mod 6? If you divide 14 by 6, you get the quotient is 2 and the remainder is 2. Then 14 mod 6 is equal to 2. So there is two different remainders. Yani 24 mod 6 does not equal 14 mod 6. Then the conclusion in they are not congruent. If طبعا the first condition is not satisfied, the second condition will not be satisfied. You will see in 6 does not divide 24 minus 14. Then the 24 minus 14 is just 10, and طبعا 6 does not divide 10. Again, يعني just like to show two integers are congruent, it is enough to show one of the conditions is satisfied. To show it's not congruent, they're not congruent, it is sufficient to show one of the condition is not satisfied. طبعا the first step when we showed in that 24 mod 6 is different than 14 mod 6, this would have been sufficient to say in the 24 is not congruent to 14 mod 6. And طبعا the usual way to negate the statement 24 is congruent to 14, the negation for that is 24 is not congruent to 14, and we use the same symbol for congruence, but just cross it as we usually do. We have two formulas that we will use. Here A, B, C, D are all integers. M is a positive integer. M is the integer, positive integer that defines the congruence. If A is congruent to B mod M and C is congruent to D mod M, the same M, then we have two rules. If you take the sum of the left-hand side, it will be congruent to the sum of the right-hand side. A plus C will be congruent to B plus D, طبعا mod the same M. Also the product of the left-hand side will be congruent to the product of the right-hand side. A times C will be congruent to B times D. Let me repeat the two formulas. A is congruent to B mod M, and C is congruent to D mod M. The sum of the left-hand side, yani A plus C, is congruent to the sum of the right-hand side, which is B plus D mod M. The product of the left-hand sides, A times C, will be congruent to the product of the right-hand side, which is B times D. The congruence here is modulo M. Here are examples. We have, and we can also check to see if the relations are correct. Is 7 congruent to 2 mod 5? Yes, then 7 minus 2 is equal to 5, which is divisible by 5. So this relation is correct. Is 11 congruent to 1 mod 5? Yes. And 11 minus 1 is 10, and 10 is divisible by 5. For now, applying the two rules, the sum of the left-hand side must equal or must be congruent to the sum of the right-hand side. That means 7 plus 11 must be congruent to 2 plus 1. 7 plus 11 is just 18. 2 plus 1 is equal to 3. Is 18 congruent to 3 mod 5? Yes. And 18 minus 3 is equal to 15. It is divisible by 5, so this relation is correct. Okay, then the first formula works. The second formula, the product of the left-hand side must be congruent to the product of the right-hand side. Yani 7 times 11 must be congruent to 2 times 1. 7 times 11 is just 77. 2 times 1 is 2. Is 77 congruent to 2 mod 5? Yes. 77 minus 2 is equal to 75, and that's divisible by 5, so this congruence is true. 77 is congruent to 2 mod 5. For these formulas, yani we will use them later. They are certainly correct. Yani they work for all integers A, B, C, D, and any M positive integer. Here is now the first application of the congruence relation, and this is cryptology. Cryptology is if you want to send a message to someone, especially if it has sensitive information, you want to encrypt it, yani change the wording of the message so that if it falls in the wrong hand, whoever reads the message will not understand or will not get any of the information. The idea, of course, is you send it to another person. The person know how you encoded the message, so they can decrypt it and read the original message. The encryption then is to replace the words or the letters of the message by other letters, so that the message will not be will not make any sense. That's encryption. Decryption is to take an encrypted message and write it back in its original form. One of the oldest and easiest encryptions is called the Caesar encryption, and that's basically each letter of the original message is shifted by 3 letters to the right. Think of the alphabet written in the order that we know, A, B, C, D, and then each letter is shifted 3 positions to the right. We like to use functions for encryption functions. For the Caesar encryption, takes every letter. Here f of p is equal to p plus 3. طبعا take the position of the letter, add 3 to it, mod 26. طبعا you have to apply the modulo 26 because the alphabet here starts with 0 for A and ends with 25 for Z. So if you add this number and you get a number more than 25, you want to still end up within the alphabet, so you take mod 26. Take the remainder when you divide by 26. For example, if you're trying to encrypt the letter Z, the number for Z is 25. The f of 25 is 25 plus 3, which is 28. Now 28 mod 26 will be 2. Okay, then Z is encrypted by the number 2. طبعا احنا to start with the alphabet A to Z, you are replacing the letters by numbers starting from 0 for A, 1 for B, 2 for C. The last letter would be 25 for the letter Z. And then they're replacing the letters of the original message by the new values. This is applying the function which represents the Caesar encryption, f of p equal p plus 3 mod 26. طبعا after you apply the encryption message, now you convert numbers back into letters. The resulting message will be encrypted. It will not make sense. The idea, of course, is a person who receives the message know the function that you used to encrypt, so they apply the inverse function to get the message back into its original form. So we will look at several examples. Here is the first example. What is the secret message that you can get from the message good morning 0? This is your original message, and we want to apply the Caesar encryptions. The first thing is, of course, is to replace each letter by the number, by its number. طبعا, as we said, the letters are numbered from 0 to 25. That is for A to Z. G is the letter number 6. O is repeated twice, is number 14. D is number 3. M is 12. O is 14. You do this to every letter, replace it by the corresponding number. طبعا this group of numbers represent the first word. The second group in the middle represent the second word, and this last group of numbers represent the third word in the original message. Now that you have applied, now is the step to apply the encryption message f of p, encryption function, sorry, f of p equal p plus 3 mod 26. طبعا if you add 3 and the number is less than 25, you use it like it is. If you get 25 or more, you can apply the modulo, يعني get the remainder after you divide by 26. Most of these numbers, when you add 3, you'll get a number less than 25. 6 plus 3 is 9, 14 plus 3 is 17, 17 again, 3 plus 3 is 6, 12 plus 3 is 15, 14 plus 3 is 17. The first time that you will get a number where you have to apply the modulo is, let's see, for this letter, 25 of course stands for Z. If you apply the encryption, 25 plus 3 is 28, so apply the modulo relation. 28 mod 26 is equal to 2. Then I divide 28 by 26, the remainder will be, the quotient will be 1, the remainder will be 2. The remaining letters are easy, and 4 plus 3 is 7, 17 plus 3 is 20, and 14 plus 3 is equal to 17. There is one more thing to do now to get the encrypted message. Replace those numbers by letters, and here is the message, encrypted message. JRRG for the first word, PRUQLQJ for the second word, CHUR for the third word. طبعا this statement here doesn't make any sense. The idea is that you can recover the original message. Now you have to apply the inverse function of f. F of x is p plus 3 mod 26. And you add 3, you shift the letters by 3 to the right. The inverse function is p minus 3 mod 26. And here, of course, you're shifting every letter to the left. If you go too far to the left, you can apply, and if you end up with a negative number, you should apply the modulo 26. You divide the number by 26 and get the remainder. If you apply the inverse function, then your encrypted message now will go back to its original form, and it will make sense. Applying the inverse function to recover the original message is called decryption. So the inverse function here is a decryption function. Let's look at another example. We want to encrypt the message, stop global warming, using the encryption message. Now this is a different message, and the Caesar encryption is not the only function we can use. We want to use the function f of x equal x plus 11 mod 26. And as usual, طبعا, the alphabet is numbered from 0 to 25, from A to Z. For the values that this function will take are those numbers from 0 to 25, representing the different numbers in the alphabet. As usual, the first step is to replace each letter with the corresponding number. Here are the numbers. The first group is the first word. The group in the middle is the middle word. The third group represents the third word in the original message. Now we do the shifting. This time it's by 11. Add 11. If you get a number which is 25 or larger, you have to apply and if you get 26 or larger, you should apply the modulo relation. Now, like for 18, if you add 11, you get 29. 29 mod 26 is equal to 3. 19 plus 11 is 30. 30 mod 26 is equal to 4. 14 plus 11 is just 25. 25 plus 11 is 26, and 26 mod 26 is 0. Most of the others will be okay, and you'll get a number less than 26. 6 plus 11 is 17. 11 plus 11 is 22. 14 plus 11 is 25. You keep doing this. طبعا يعني applying this function, adding 11, and طبعا if you get a number 26 or more, you have to apply the modulo relations, يعني divide it by 26 and use a remainder. طيب, the final step now, you have to replace each letter, each number by a letter, and here is the encrypted message, which again, it does not make any sense. And now the person who receives this message must apply the decryption function or the inverse function of f. In this case, f inverse of x should be x minus 11. The shifting should be to the left. Here is an example where we're asked to decrypt a message. طبعا to decrypt a message, you have to know the decryption function. Sometimes you're not given the decryption message, you are given the encryption message. So before you decrypt the message, you have to find the inverse function and then apply it to the encrypted message. Here is the statement that consists of 3 words we want to decrypt. Knowing that we used the function f of x, which is x plus 7, to encrypt the original message. And in the original message, we used the encryption function f of x equal x plus 7, and the encrypted message we obtained is given to us in the problem. Then the decryption function must be f inverse of x is x minus 7. The process now, take the encrypted message, replace the number, each letter by its corresponding number, and here are the numbers. Now apply the inverse function of f, which is the decryption function, and here are the numbers you get. We won't do the details. I think we did at least 2 other problems, but these are the numbers after you apply the decryption function, which is f inverse of x is equal to x minus 7. We can do some. 11 minus 7 is 4. 4 minus 7 is minus 3. Take that mod 26. The result will be 23. Do this to every number. And as usual, the final step طبعا to decrypt is replace the numbers by letters, and the result will be experience is a great teacher. طبعا one clue that you should have, if you start with a decrypted message, it probably will not make any sense. Now, if you are asked to decrypt it, the result should be a message that makes sense. If you end up with something that doesn't make sense, then you probably made mistakes in the decryption process. The decrypted message should be a message that makes sense. Here is another application. It's actually an optional application, but we can go ahead and do it. A computer has only 20 memories. This is how you can use the congruence relation to decide how to store different numbers. So let's assume now you have a computer with only 20 memory locations from 0 to 19. The hashing function is actually uses a congruence function relation, and the hashing function will tell you where to store any number. h of x is equal to x plus 5 mod 28. طبعا the images or the range or the values you will get from this function will all be from 0 to 19. 0 to 19. فطبعا إذن every number will always be stored in one of these locations. Whatever you get by applying the hashing function, that will tell you where to store the number. For example, where would you store 57? h of 57 is 57 plus 5 modulo 20, which will give you 17. I'm reading the wrong line. h of 57 is 57 plus 5 mod 20, which is 62 mod 20, which is equal to 2. 57 is stored in memory location number 2. H of 32, you add 5, you get 37. 37 mod 20 is just 17. 32 is stored in memory location number 17. H of 98 is, when you add 5, this is 103. 103 mod 20 is 3. 98 is stored in memory location number 3. Next, we would like to look at prime numbers, define what prime numbers are, and also see how to calculate the greatest common divisors of integers. The definition for a prime number: a positive integer p greater than 1 is a prime if and only if the only positive factors of p are 1 and p. We only consider now positive integers greater than 1 to be a prime number. And a number is considered to be a prime number if the only factors are the number itself and 1. In another way, you can say that p is divisible only by itself or by 1. Here are the first few prime numbers. 2, of course, is the first prime number. Then 3, 5, 7, 11, 13, 17. And طبعا this set is infinite. There is an infinite number of prime numbers. One thing we will notice about prime numbers that 2 is the only even prime number. All the remaining prime numbers will be odd. Non-prime integers greater than 1, any number that is greater than 1 and not an integer, not a prime, is called a composite. It's called a composite because they can be composed by multiplying 2 integers greater than 1. Here is any integer greater than 1 is either a prime, in case it can only be divided by the number itself, or by 1. The only factors are the number itself and 1. If the integer greater than 1 is not a prime, then we will call it a composite number. With the idea of a prime number, we can now study the fundamental theorem of arithmetic, which says that every positive integer greater than 1 has a unique representation as a prime or as a product of 2 or more primes, where the prime factors are written in order of non-decreasing size. Then every positive integer either will be a prime. If it's not, then you can write it as a product of 2 or more primes. And of course, you can always write the factors in non-decreasing order. The thing here is anytime you write an integer as a product of its factors, prime factors, this representation is unique. Provided you write it in a non-decreasing order, there is only one way to factor an integer, to write it as a product of its prime factors. Here are examples. 100 can be written as 2 times 2 times 5 times 5. Anytime you have a repeated factor, you can write it as a power. So this is 2 to the power 2 times 5 to the power 2. Notice we wrote the factorization in increasing order. Then this is the prime factorization of 100. 2 to the 2 times 5 to the 2. There is only 2 prime numbers in the factorization, but they are raised to a power. 641 happens to be a prime, so there's only one way to write it, is write it as itself, 641. 999 can be written as 3 times 3 times 3 times 37. So this is 3 cubed times 37. 37 is a prime. The number 1024 has only one prime factors, but it's repeated 10 times, and it's 2 multiplied by itself 10 times. So the prime factorization for it is 2 to the 10. Here is a theorem that we can use to factor integers. If n is a composite integer, then n has a prime divisor less than or equal to the square root of n. For example, 49, the prime numbers less than the square root of 49 are 2, 3, 5, and 7. And the only factor in 49 is 7. For 16, the prime numbers less than the square root of 16 are 2 and 3. And of course, 16 has only one prime factor, which is 2. One way then to use the theorem is to show that a number is a prime if it's not divisible by any prime less than or equal to the square root of n. That means we don't need to check all the primes less than n. It is sufficient to check the primes that are less than or equal to the square root of n. Here is a quick example. For 13, the square root of 13 is approximately 3.6. The only two primes less than this number are 2 and 3. 13 is not divisible by 2, it is not divisible by 3, and therefore 13 is a prime. But here are the factors based on the theorem. To find the prime factors for an integer, first find the square root of n, then list all the primes up to the square root of n, and then find all the prime factors that divide n. What we do is we try them in order, starting from 2, then 3, and 5. If a number divides the integer, if one of those primes divide the integer, then it will be a factor. But the point here is you don't need to try all the primes up to n, just look at the primes up to the square root of n, and by using these prime factors, you'll be able to find the prime factorization. Here is an example to show 100 is a composite. The square root of 100 is 10, but the only primes less than 10 are 2, 3, 5, and 7. If you try the first number, 2, 100 is divisible by 2, and therefore it is not a prime, therefore it is a composite. 101, we can show that this is a prime. The square root of 101 is approximately 10, so the prime numbers are 2, 3, 5, and 7. It is easy to show that 101 is not divisible by 2. Actually, the remainder will be 1 in this case. It is not divisible by 3, not divisible by 5, and not divisible by 7. And therefore, 101 is not divisible by any prime less than or equal to the square root of 101, and therefore 101 is a prime. Here is another example to find the factors. We want the prime factors for 7007. The square root of 7007 is approximately 83. So we only list the prime numbers up to less than 83. All the primes that are less than 83, and then start by dividing to find the factors. We will see the number is not divisible by 2 or 3 or 5. The first number that divides is 7. 7007 divided by 7 is equal to 1001. So here is our first factor. Now the quotient here may still be divisible by 7. So we divide again by 7. 1001 divided by 7 is equal to 143. So this prime factor is repeated. So this is the second factor in the prime factorization. Now the quotient 143 will not be divisible by 2, 3, 5, or 7. The first prime that divides it is 11. So 143 divided by 11 is equal to 13. معناته 11 is now our next prime factors. Finally 13 is divisible by 13. And that's the final division. Once you get 1, there is no more division. Then the factors are 7 twice, 7 times 7 times 11 times 13. And of course, the repeated factors are written as a power. So the prime factorization of 7007 is 7 squared times 11 times 13. Now we can define the greatest common divisor, and that is we try to find it for two integers. For the definition of the greatest common divisor, or GCD for short, the GCD of A and B, where A and B are integers, طبعا they can't be both 0. The GCD is the largest, most positive integer, D, that's a divisor of both A and B. طبعا greatest common divisor, so it will be a common divisor, and it divides both A and B, and it is the greatest integer that does that divides both A and B. طبعا we can apply the definition to find the GCD, or the second method that we will see is using the prime factorization. Here is a method to apply the definition. Find the GCD for 24 and 36. Try to find all the divisors of 24, and they are listed 1, 2, 3, 4, 6, 8, 12, and 24. The divisors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. The common divisors, the integers that divide both numbers, are 1, 2, 3, 4, 6, and 12, and 12 is the largest such integer. Then the GCD of 24 and 36 is equal to 12. This is finding the GCD of two integers applying the definition, but the method that we like to do is using the prime factorization, which we will do in the next slide. Using the prime factorization, you can do it by taking the minimum power of common factors. Anytime there is a common factor, take the minimum power and then multiply these minimum factors, minimum powers for factors, for the common factors, multiply them by each other, and that will give you the GCD. Here is an example. We want to find the GCD of 24 and 180. The first step is to write the prime factorization. 24 can be written as 2 to the power 3 times 3. 180 can be written as 2 squared times 3 squared times 5. Now we want to take the minimum power of common factors and multiply them by each other. For the 2, the minimum power is 2 squared. For 3, the minimum power is just 3, and that's it. There are no more common factors. So we take 2 squared times 3 to the 1, and that will give you 12. And that will be, طبعا 12 is the greatest common divisor of 24 and 180. Here is another example. We want to find the GCD of 360 and 3500. The first step is to factor. 360 can be written as 2 to the power 3 times 3 squared times 5. 3500 can be written as 2 squared times 5 to the power 3 times 7. The GCD, we want to take now the minimum power of common factors and multiply it by each other. For 2, the minimum 2 is a common factor, so we take 2 to the power 2. طبعا the 3 is not a common factor. The 5 is the next factor. The minimum power of 5 is equal to 5 to the 1. The two common factors are the 2 and the 5. For the 2 we take 2 squared. For the 5 we take 5 to the 1. Multiply those numbers, you will get 20. The greatest common divisor of 360 and 3500 will be 20. Here is another example. Find the GCD of 17 and 22. Notice 17 is a prime. طبعا 1 will always divide both integers, but unless the second integer is divisible by that prime, 1 will be the only number that divides both. There are no common divisors other than طبعا no prime divisors. For the GCD of 17 and 12 is equal to 1. 1 is actually the only number that would divide both. Of course, it's not a prime number, but it is the only number that divides both integers. In this case, what we say is, the terminology we use in this case is that the numbers 17 and 12 are relatively prime. Relatively prime meaning the GCD of the two integers will be equal to 1. Now, least common multiple, first of all, a common multiple for two integers a and b will be a number that's a multiple of a and also a multiple of b. There could be several. If you take the product a-b, will be a multiple of both. There could be several common multiples. We pick the least, and that gives us the least common multiple, or the LCM of a and b. Then, by definition, the LCM, the least common multiple of positive integers a and b, is the smallest positive integer that is a multiple of both a and b. For example, we want to find the least common multiple of 6 and 10. Here, using prime factorization, take the maximum power, this time of all factors, not just the common factors. For any factor, take the maximum power for all factors and multiply them by each other. Here's an example for 6 and 10, of course. 6 is just 2 times 3. 10 is equal to 2 times 5. Take the 2, take the 3, and take the 5. Multiply these three integers. You will get 30. That is the least common multiple of 6 and 10. It will be a multiple of 6 and a multiple of 10, and this is the smallest integer that is a multiple of both numbers. Here is another example. Find the LCM, the least common multiple of 24 and 180. Start by writing the prime factorization. 24 is 2 to the power 3 times 3. 180 is 2 squared times 3 squared times 5. Now take the maximum power of all factors. With the 2, you need to take 2 to the power 3. With the 3, take 3 squared, and also take the 5. The product of these three numbers will equal 360. 360 is the least common multiple of 24 and 180. Integers and algorithm. We will now consider another application that deals with how we represent numbers. The way that we are used to representing numbers, something we learn from an early age, we call that the decimal representation, in the sense that every integer in the representation of a number is just a multiple, or is a number multiplied by some power of 10. So we can think of this system as based on the number 10. We will see that there are applications where we could represent the numbers using a base other than 10. This is what we will do. We will see how to represent numbers in many bases, such as the binary representation. Here the base will be 2. We know that, for example, the binary representation is the basis for computer arithmetic. Will be our subject, is to see how we can write numbers, how to represent numbers in different bases. Again, the system that we use the most in everyday life, we use the decimal notation. We use a number system based on the number 10, or the decimal notation. Here, for example, the number 965, the first digit 5, from the right to the left, 5 is multiplied by 10 to the power 0. Then the second number is the tens, but this is 6 times 10 to the 1. The third number 9 is 900, so it's 9 times 10 to the power 2. For every digit in the decimal representation is multiplied by a power of 10. Starting with the 0 power, the power 1 and power 2. The power seems to be 1 less than the location of the digits. مثلا 5 is multiplied by the 0 power. The second digit is multiplied by the power 1. The third digit is multiplied by power 2. For the power is always 1 less than the location of the digit. This is the system we are used to. This is the decimal notation, or this is a number written using the base 10. We will see it is convenient to use, sometimes we should use or can use bases other than 10. Using this model, we can see about representing numbers using bases other than 10. For computers, some of the bases that are used the most are the binary meaning 2 digits, or 2 is the base, when carrying out arithmetic. Arithmetic in computers is done using the binary notation. There is also the octal, which is base 8, and the hexadecimal, which is base 16. These are used to express characters. Characters could be numbers, letters, and many other things. Base 2 is used for arithmetic. Base 8 and base 16 is used to express characters. We can use any positive integer greater than 1 as the base. Those bases happens to be used more in computers, but any digits greater than 1, any integer greater than 1 can be used as a base. The binary notation or representation uses base 2. For any number you write in a binary notation would be now multiplied by a power of the base, which in this case it will be 2. Since we are working with base 2, there's only 2 digits present, the 0 and the 1. Here is an example of a number written in binary notation, and we write the base, and we enclose it in parentheses and write the base to the right of that. This numbers consisting of zeros and 1 is a number written in a binary expansion. To convert it to base 10 or decimal expansion, you want to multiply each digit by a power of 2, depending on the location. I like to start from left to right, but you can start from right to left. For example, the digits to the far left, there is 9 digits, so this is the 9th digit, so this is multiplied by the base to the power 8. It's multiplied by 2 to the 8. The next digit, 0, is multiplied by power 7, 2 to the 7. Third digit is multiplied by the power 6. So you keep doing this. By the time you reach the farthest integer to the right, 1, is multiplied by the power 0. That's how you can do it. You know that the base is 2. For every digit is multiplied by a power of 2, depending on the location. Starting with the 9th location, this is power 8. The next one is 7, 6, 5, until you reach the 0 power, which is the digits to the far right. Okay, for the next thing, you evaluate. Some of these will be 0, but if you evaluate those powers and add all those numbers, the result is 351. For the result now is given in decimal notation. The binary digit we started with, this number is in base 2, converted to decimal notation, it will be the number 351. The next base we'll look at is the hexadecimal, which is base 16. In base 16, the first 9 numbers are the same as the decimal notation, and 0 to 9. Then past this point, we use letters. The number 10 is represented by A, 11 is represented by B, 12 is C, 13 is D, 14 is E, and 15 is F. طبعا there is 16 digits starting from 0 to 15. طبعا 15 here is represented by F. For the first 9 digits are the same as the decimal. The 10th to the 15 digits we use letters A through F. This is the hexadecimal system, and we will look at an example. What are the decimal expansions of the hexadecimal number? The first number is base 16, and the second number is base 7. These are two separate conversions. For the first one, since this is base 16, every number is multiplied by a power of 16, depending on the location. We have 1, 2, 3, 4, 5. For the 2, which is to the far left, is multiplied by a power 4, the base raised to the power 4. For the 2 is multiplied by 16 to the 4. The next number A is just 10, and that's multiplied by 16 to the power 3. The next number is E, which is 14, and that's multiplied by power 16 to the power 2. The next number, which is 0, is multiplied by 16 to the power 1. The last number, B, is 11, so it is multiplied by 16 to the power 0. If you do the calculations, you should get 175,627, and that's the number in base 10. The number we started with in base 16 is equivalent to the number 175,627 in base 10. The second problem, this is base 7, so we're multiplying now by powers of 7. Starting with the 3, this is in 4th position, so it's multiplied by 7 to the power 3. The 0, the second digit, is multiplied by 7 squared. The 1 is multiplied by 7 to the 1, and the 6 is multiplied by 7 to the 0. And doing the calculations, we should get 1042, and this number here will be base 10, or the decimal representation. Let's see how we can convert to from a decimal number into another base. In this case, we will start by converting a decimal number, or number written in decimal notation, to binary notation. Find the binary expansion of 241. 241 here is a number written in decimal notation. To convert a number from decimal to any base, you divide by that base and take the remainder. In every step you take the remainder. If I start by dividing 241 by 2, the quotient is 120 and the remainder is 1. But the 1 here now becomes your first digits to the right. This is the digit 1 in the binary representation. Take the quotient now, 120, and divide again by 2. You get 60 and the remainder is 0. And that's your second digits in the binary notation. 60 is equal to 2 times 30, and the remainder is also 0. So this is your third digit in the representation. 30 is equal to 2 times 15. The remainder is 0, so this is the third 0, or the fourth digit. 15 divided by 2 equals 7, and the remainder is 1. So you get the first one. 7 is equal to 2 times 3 plus 1, so the remainder is 1. That's your second one. 3 is equal to 2 times 1, and the remainder is 1. But that's the third 1. And finally 1 divided by 2, you get the quotient 0, and the remainder is 1. You have to keep dividing until you get a quotient of 0. In the last step here, the remainder is 1. That gives you the final digit of the binary representation. But again, what you do is the number you are trying to convert to base 2, keep dividing by 2, and take the remainder to be your digits, to be your binary representation. These numbers are written from right to left. The first remainder gives you the first digits from the right. The second remainder gives you the second digits from the right. You keep doing this until the last remainder, which is when you get a quotient of 0, that will give you the last number in the binary representation. Then the number 241 in decimal notation is equivalent to 11110001 in base 2. Here is now converting a number to base 8. Starting from the number 12,345 in base 10, I want to convert it to base 8. So now we divide by 8, the base, and take the remainder to be my digits from right to left. For the first time we divide by 8, we get the quotient is 1,543 and the remainder is 1. But the remainder here becomes your first digits from the right. 1,543 divided again by 8, you get a quotient of 192 and the remainder is 7. And that's your second digits in the representation, in the octal representation. 192 divided by 8 is 24 and the remainder is 0. That's the first 0 in the representation. 24 divided by 8, you get 3 and the remainder is also 0. That gives you the second 0. Finally, the 3, when divided by 8, you get a quotient of 0 and the remainder is 3. And that's your final digit in the representation, in the octal representation. So the number 12,345 in base 10 is equivalent to 30071 in base 8. Let's do now start with a number in decimal notation and convert it to hexadecimal, base 16. But here now you always divide by the base. Divide this number by 16. The quotient is 11070 and the remainder is 10. 10 is the first number from the right. 10 is equivalent to 10 to A in base 16. So this is your first number. 11070 divided by 16, you get 691 and the remainder is 14. And 14 is just the letter E. So that's your second number. 691 divided by 16 is equal to 43 and the remainder is 3. And that's your third digits in the hexadecimal expansion. Next, 43 divided by 16, you get the quotient is 2 and the remainder is 11. 11 is equivalent to B in base 16. The last step is when you get a quotient of 0. 2 divided by 16, you get a quotient of 0 and the remainder is 2. And that's your last digits in the representation for base 16. Our number that we started with, 177130 in base 10, is equivalent to 2B3EA in base 16. The last slide, for special bases, there is another method that you can use, and these are only if the base is a power of 2. There is another method to convert, for example, from base 8 to binary, from hexadecimal to binary, or from binary to hexadecimal or to octal. But this is based on the fact that these powers are all powers of 2. For the way to do this, we will look at some examples. If you want to convert from octal to binary, from base 8 to binary, first you notice that every digits in the octal representation can be represented by 3 digits in the binary notation. For example, the number 0 in base 8 can be written as 000. The number 1 can be written as 001. Number 2 is 010. 3 is 011. 4 is 100. 5 is 101. 6 is 110. 7 is 111. But now to convert a number from base 8 directly to base 2, just replace each digit in base 8 by its equivalent, and replace it by 3 digits which are equivalent, and this is from the table. For example, 7 can be replaced now by 111. The digit 0 can be replaced by 000. This is the first line in the table. And the number 3 can be replaced by 011. For here, the result here gives you the same number in base 2. This is just done in one step by replacing each digit in base 8 by the 3 digits which are equivalent to it in base 2. To convert from base 16 to base 2, you need a table like this, where each digit in base 16 is replaced by 4 digits in the binary system. Let's just do some of them. Like 0 is just in the base 16 is 4 zeros in the binary system. Let's look at more numbers. For example, the number 6 is 0110. The letter A, the number A, is 1010. For each digit in base 16 can be replaced or is equivalent to 4 digits in the binary system. So we do the same thing to convert from base 16 to base 2, is replace each digit in base 16 by the 4 digits that are equivalent to it from base 2. For example, 7 is equivalent to 0111. So 7 is replaced by those 4 digits, 0111. B is equivalent to 1011, where the B is replaced by 1011. Finally, the 5 is equivalent to 0101, where the 5 is replaced by 0101. For the result will give you the representation of the number in the binary notation. Now to convert back, for example, if you want to convert from base 2 to base 16, you know each 4 digits in base 2 is equivalent to 1 digit in base 16. For the first step, to take the number in base 2 and write it as groups of 4. You go from right to left and separate the numbers into groups of 4s. If you end up with less than 4, you can replace by 0. For example, if you take them in 4s, you are left with 101. Just add 0 to the left. That will not change the number. So now you have your original number in base 2 is divided into groups of 4. Now replace from the same table, replace each 4 digits in base 2 by 1 digit which is equivalent to it from base 16. For example, the first group, 1101, from the table is equivalent to D. 1101 is equivalent to D, so you can replace it by D. The next group, 0011, is equivalent to 3, so just replace it by 3. The final group, 0101, is equivalent to 5. Here it is 0101 is equivalent to 5, so just replace it by 5. This conversion gives you the number in base 16 in one step. Here is more examples. You can here there is conversion from base 2 to base 8, also from base 8 to base 2, or from base 2 to base 16. And using those two tables, from octal to binary, what you have is each octal number is replaced by 3 digits in the binary system. For the hex and binary, every hexal digits is replaced by 4 digits. So just using those tables, you can do the conversion يعني directly between those bases.